Hello everyone. In this video we look at one of the important concepts related to the idea of equilibrium, which is reaction quotient. Now we'll talk about first what is this reaction quotient, and then we'll try to understand what is the significance of this in the study of chemical equilibrium. So let us say we have an equilibrium reaction which is given, PCl5 gas decomposing to give PCl3 gas and then Cl2 gas. Now at the equilibrium stage we relate the concentrations of the products, which is PCl3 and Cl2, to the concentration of the reactant, which is PCl5, to get this equilibrium constant Kc. So Kc will be the product concentrations, each of them raised to the respective powers, divided by the reactant concentration. Of course here all the powers will be 1, so Kc value will be equal to the Cl2 concentration into PCl3 concentration by PCl5 concentration. Now these concentrations are the concentrations of reactants and products at the equilibrium stage. Now if the reaction is not at equilibrium, means we are proceeding with the reaction towards equilibrium. It is at some intermediate stage. Intermediate stage will mean it is at some particular stage. They have not yet reached the equilibrium. Then we take the same ratio, just like the equilibrium constant, we take the same ratio of Cl2 concentration into PCl3 concentration by PCl5 concentration. This ratio is what we call as QC, reaction quotient expressed in terms of concentrations. Now we can say QC is the general term used for the above ratio or the particular ratio at any given instant of time. Now the difference between QC and Kc is, for Kc we will use the concentrations at the equilibrium stage, and QC would be by taking the concentrations of reactants and products at any given stage. And of course when we are already reaching equilibrium, we see that the value of QC will be simply equal to the equilibrium constant Kc. So this is how we will define the reaction quotient in concentration terms. Now similarly for the gas phase reaction, of course the example we took itself is a gas phase reaction, we can even have Qp, which is expressed in terms of the pressures of the gases. Now just like the way we have the Kp, so Kp is nothing but the pressure of Cl2 into pressure of PCl3 by pressure of PCl5, but all these pressures are measured at the equilibrium stage, and we take the same ratio of the pressures at any given stage, then that is what we call as reaction quotient expressed in terms of pressures. Now if we are not at the equilibrium stage, we will refer to that particular ratio as Qp. If we already are at equilibrium, then we know that Qp value will be equal to the equilibrium constant Kp. So this is about the two kinds of reaction quotients which are defined on the basis of the ratio of product concentrations to the reactant concentrations, or the ratio of the product partial pressures to the reactant partial pressures, just like the equilibrium constants Kc and Kp. Now when we look at the significance of this reaction quotient Q, so we can generally call it as Q, and when we compare the value of Q with K, of course we have to keep one thing in mind. If you are talking about Kc, then we will be referring to Qc. If you are talking about Kp, then we will be referring to Qp. The comparison of the two will help to determine the direction in which a given reaction will proceed from the particular stage of the reaction. Means, when we are moving towards equilibrium, so one thing that we need to understand is any equilibrium can be arrived at from both sides. So we may be able to arrive at the equilibrium from the reactants side to the equilibrium stage, or we may even arrive at the equilibrium from the product side. So when we are moving from reactant side to the equilibrium, we basically call it as the forward, and when we are moving from product side to the equilibrium side, we will call it as a backward. So the comparison of Q value and K value will help in determining whether the reaction is going to proceed in the forward direction or reverse direction from the given stage. Now as we already discussed, if the value of Q is equal to K or Kc, assuming that we are referring to the parameter using the concentration terms, then it would mean that we are already at the stage of equilibrium. And there will be two more possibilities. Either Q will be less than K or Q will be more than K. Now if we have Q less than K, then the net reaction will proceed from left to right. So here when we say left to right, what we are essentially talking about is the reaction will proceed from the reactant side to product side. That is what we basically call as the forward step or forward direction. Now why we are concluding that if the Q value is less than K, the reaction will proceed in the forward direction. Now when we look at the Q or K for that matter, in numerator we have the product concentrations or product partial pressures. Now if the value of Q is less than K, it would mean that the proportion of product amount at that given stage is lesser than proportion of the product at the equilibrium stage. So this is basically the proportion of the product at the equilibrium stage. Proportion of the product at the given stage is lesser than proportion of the product at the equilibrium stage, which means from that particular stage we will be able to form some more product, so that we will be able to increase the proportion of the product, and that would happen only when the reaction is proceeding in the forward direction. So if you would want to increase the proportion of the product, then that would be possible only when the reaction is moving in the forward direction. Now the other possibility is that Q is already more than K. If Q is already more than K, then net reaction proceeds from right to left. So if you look at it, on the right side we'll talk about the products, and left side we have the reactants, which means it is moving from right to left. We say it is in the backward direction or the reverse direction. Now why we are concluding that if the Q value is more than K, the reaction will proceed in the backward direction? Again, if we look at the K, we will have product concentrations or product partial pressure in the numerator, and Q, again we have product concentrations or product partial pressures in the numerator. Of course for Q it is at the given stage. Now when we say Q value is more than K, it would mean that the product is in a higher proportion than what it is to be at the equilibrium. Means some more product has to be consumed, so that at the product proportion of product amount will be decreasing, and this is only possible when the reaction is proceeding in the backward direction, because when the reaction proceeds in the backward direction, some amount of product will be consumed and reactant will be getting formed. So this is about the significance of the reaction quotient, which will help us in knowing from the given stage in what direction the reaction will proceed. Now we'll try to understand this with the help of an illustration. We have an equation which is given to us, which is A plus B giving rise to 2C. All are gases, and at 25 degrees centigrade in a 2-liter vessel we have 1, 2, 3 moles of these substances respectively, which would mean that we take the number of moles of A is 1, B is 2 and C is 3. Now we need to predict the direction of the reaction under these 3 cases, when Kc is 3, when Kc is 6 and when Kc is 4.5. But before we go on to understanding these 3 cases, let us first look at what are the concentrations of A, B, C at the given stage. So number of moles of A is 1 and the vessel volume is 2 liter. So concentration of A will be 1/2 molar unit. Concentration of B will be the number of moles of B is 2, and again the volume over here is 2 liters, so it will be 2 by 2, which is 1. And the concentration of C, number of moles is 3, volume of the vessel is 2 liters, so it will be 3 by 2. These are the molar concentrations. And at the given stage, if we look at what is the Q value, reaction quotient, it will be the molar concentration of C power 2 by molar concentration of A into molar concentration of B, which will be 3 by 2 whole square by molar concentration of A is 1 by 2 into 1, which is 9 by 4 divided by 1 by 2. So 2 ones are 2 twos are. Finally we have 9 by 2, which is 4.5. So based on the given amounts of A, B, C, the reaction quotient value for the given reaction is 4.5. Now let us come back to the three cases given. First case, Kc is given to be 3. Now if Kc is 3, what we have over here is Q value is more than K, because Q value is 4.5 and K value is 3. Now if Q is more than K, then the reaction will proceed in the backward direction or the reverse direction. Look at the second case. When K is 6, if K is 6, Q is only 4.5. So what we have is Q is less than K, because Q is 4.5 and K is 6. Then we will see that from that given stage the reaction has to proceed in the forward direction. The third case is Kc value is given to be 4.5, which is a case where we exactly have Q is equal to K, both are 4.5. Then this is already at the equilibrium stage. So from here the reaction will neither proceed in the forward direction nor proceed in the backward direction. So this is about the importance or significance of reaction quotient in the study of chemical equilibrium.